This next unit is going to be Chapter 12, and what we're talking about in this unit is defining and using sequences and series. You're going to have to pay very careful attention to vocabulary here because there's a very slight difference between a sequence and a series, and I want to make sure you catch that. Okay. Here's what we want to know about sequences. A sequence is basically a function. It's a pattern you can get from one term in the sequence to the next. But what's special about a sequence is the domain. Remember, that's our inputs. The domain is a set of consecutive integers. Consecutive meaning in a row. Integers, we're talking about negatives and positives, but only like not decimals. -1, -2, -3, or 0, 1, 2, 3, ... Those would be the integers. The values that are in the range, the output, are the terms of the sequence. So, for example, the domain is 1, 2, 3, 4. That's describing the relative position of each term, meaning first term, second term, third term, the order that they come in. And then the range is the terms of the sequence. So that would be, if we call those terms A, it's going to be A1, meaning the first output, A2, meaning the second output, and so on. A1 goes with term 1. A2 goes with term 2. Okay? Now, we see two different types of sequences. We see a finite sequence that has a limited number of terms. It has a start and a finish. You won't have any terms beyond or before that. Or we can have an infinite sequence that continues without stopping. A finite sequence, for example, would be the sequence 2, 4, 6, and 8. That's it. There are no other terms. If we followed the pattern, 10 would be next, but it's not included in this one because it's a finite sequence. An infinite sequence follows the pattern on forever. So we'd have 2, 4, 6, 8, and on and on and on. 10, 12, 14, 16, and so on. Okay? And just like with any equation or function, we can specify a rule or an equation. There's a typo there. It should say for, not fro. But for example, both of those can be described by the rule a sub n, meaning the nth term, however high we want to go, a sub n equals 2n. In the notation that we've been used to, we would say f of n, the output, is equal to 2 times n. I don't want to see this f of n notation in this unit. We will really be working on using this function, this sequence notation using the sub numbers to specify the number in the sequence. Okay, so how do we evaluate a sequence? Whoops, I went one too far. Okay, how do we evaluate a number in a sequence? Here's a couple of different examples. The first one tells us that a sub n, meaning the nth term, however high we want to go, is equal to 5n minus 1. We want the first 5 terms. So we can list them out this way. And to practice getting used to this notation, I want to see you use it. So we're going to have a sub 1, that's our first term. Because the relative position here is 1, it's our first term. That's what we're going to put in for n. So 5 times 1 minus 1, which is 4. A sub 2 would be 5 times 2 minus 1, which is 9, and so on. We want the first 5, so we'll keep going this way. Times 3 minus 1 equals 14, and you would keep going. And ta-da, here's all 5. So the first 5 terms in our sequence would be 4, 9, 14, 19, and 24. Okay, go ahead and try the next one and see if you can come up with that on your own. Go ahead and hit pause while you try to work it out. Here's the answer that you should have gotten, so you can check your answer. If we list all of these out, the first 5 terms would be -1, +1, 5, 13, and 29. All right. Now, we also can look for patterns and be able to see come up with our own rule for that specific sequence. These are the hardest ones, and in this first unit, they really want you to start thinking about patterns and recognizing different types of numbers on your own. As we progress in this unit, you're going to have some tricks kind of up your sleeve to make this a little bit easier. But what I noticed right away for this first one, and these are just the kind of numbers you want to be thinking about, good ones to look for are perfect squares, even numbers, multiples of a number. And along that same lines of perfect squares, I noticed that this first one are the perfect cubes. If you look at the chart on the wall, this is the n to the third column. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and so on. But we need this to be negative. And so we would take whatever we get cubed, n cubed, and then we're going to take the opposite of that, or multiply it by -1. So that would be the rule that we would get. We need to make sure that we use that sequence notation, meaning the nth term is equal to the opposite of the term number cubed. So if I wanted to know the 25th term, I would plug in 25 for n. Okay, so the rule for the nth term in this one means whatever term number I want, I cube it. This next one is kind of hard, so I want to show you a little bit of a trick. Because these are actually functions, they just have the integers as their domain, we can use a lot of the same rules that we've used before. We looked at, when we did linear and quadratic, we looked at that idea of finite differences, and we said that if a function has a constant rate of change in the output, that means it's going to be linear. You'd have an n to the first. If my function has a constant rate of change in the second difference, then that would mean that it would be a quadratic. So here's what I look at. I look at the differences. I don't notice a pattern right away here, so I say to get from 0 to 2, I added 2. From 2 to 6, I added 4. From 6 to 12, I added 6. There's no constant difference there yet. There's a pattern, but there's not a constant difference. I didn't get plus 5, plus 5, plus 5, or something like that. But if I were to do this again, I get plus 2, and we can guess that that would continue on this way. When you get a constant second difference like this, that tells us that we're going to have a squared term in our relationship here. So that kind of helps me to know where to start. So I might start with just n squared. If I do that, what's 1 squared? 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. Well, how do I get from what n squared gives me to what I want? I look at that and I say, okay, to get from 1 to 0, I'd have to subtract 1. To get from 4 to 2, I would subtract 2. 9 to 6, I'd subtract 3. 16 to 12, I subtract 4. I notice that what's happening is I'm subtracting the term number each time. When it was the first term, I subtracted 1. The second term, I subtracted 2. The third term, I subtracted 3. What is it that stands for the term number? That's what n represents. We take n squared and we subtract 1 from it. And that's how we get our sequence here. These are hard. I would be expecting you guys to get a simple pattern like adding something, multiplying something, dividing something, or to recognize numbers like perfect squares, perfect cubes. I would expect you all to be able to figure out something like that. One like this, I don't know that I would give you one like that probably on a test until we had practiced these a lot more. Okay, I'm going to go ahead and go on to the next example here, the next bit of information. Oops, hold on. Okay, now here's the difference between a sequence and a series. When you add up all the terms of a sequence, that's when we stop calling it a sequence and we call it a series. A series contains addition and only ever addition. Okay, so if we consider that sequence that we started off with, 2, 4, 6, 8, if I add those up, 2 plus 4 plus 6 plus 8, now it's a series and no longer a sequence. Okay, just like with sequences, we can have a finite series or an infinite series. An infinite series would say 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14, on and on and on forever. Believe it or not, we can approximate the sum of an infinite series. There's a lot of math that went into lots and lots of years of work to be able to prove these, but it works. So this summation notation, which you were exposed to a little bit in the last unit, we can use that to write out these series. Now, I want you to look at this, and it's kind of small on here, but in your paper, you can read it a little bit better. What we have is we're going to tell this big giant E tells us that we're going to use summation notation. Notice that the variable here and the variable here match up. They have to, because it's telling us what we should put in for our i's. Now notice this says I equals 1. This is telling you the number to start with. And here it tells us 4. That means to stop at I equals 4. So we would do plug in 1, plug in 2, plug in 3, plug in 4, and then we're done. Because that was how high up it told us to go. If you look at this other one, notice that the top number here is infinity. That's what the sideways 8 means if you haven't seen that before. And so that means keep adding up until you run out of time, because you'll go on forever. Another way that we refer to this, the start and the stop, is we have our lower limit and our upper limit. Okay, so let's look at something like that. So we want to write this using summation notation, and I'm just going to do a couple of these here so you can kind of see the idea. This is very similar to what we did with the sequences. However, we're going to be using that Greek letter sigma. If we look at this first one, ignore the addition for now. What is the pattern? For this first one, 25, 50, 75, on and on and on, I notice that this is adding 25 each time. That's kind of an easy one. And so we're going to keep doing that. So this would be, we start with 1, 2, 3. Remember, these are our term numbers. We have to figure out, how do I get from my term number, what do I do to it to get 25? Well, 1 times 25 is 25, 2 times 25 is 50, 3 times 25 is 75, and so on. So we know that the pattern that we're following is 25 times I, or n. You don't have to use I. You can use any variable there. I don't know why I is typically the one we use. It just is. But 25I, I being the term number, the position number in the sequence. So we started with 1 times 25. So we're going to start with I equals 1. Now the question is, how far up do we go? Well, 250 is 25 times 10, so that means that we will go up to 10. And this is how we would write this using summation notation. B is kind of an interesting one. It gets a little bit different as we go along. Remember, we're comparing this to the term number. First term, second term, third term, fourth term, and this one is going up to infinite number of terms. Well, I notice right away that the top of the fraction matches my term number. So that's going to be the top of my fraction. What do you notice about the bottom of your fraction? I notice that it's 1 more than whatever the top is. 1 goes to 2, 2 goes to 3, 3 goes to 4. So that would be n plus 1 in the bottom. Did we start with 1? 1 over 2? Yes, we did. So now notice, since I wrote this formula with n's, that's the variable I need to use down here. I'm going to start with n equals 1, and then this time we're going up to infinity, so that's what's going to go on the top. Okay? I'm going to let you go ahead and try these second two on your own. One is a pattern that we've already talked about, and then hopefully you can figure out the last one. Give yourself a little test here, and you can pause it, and you'll have the answers here in just a second. Okay, and here are the answers. For part C, I noticed that those, again, are all the perfect cubes. This time it goes all the way up till 9. So I used K this time just to kind of show that you could use a different variable. And then with D, I noticed that the change every time was 1. But if I was going to do that, oh, there's my dog. Sorry, he must have heard something outside. So the term number I start with is 5, but do you know what I just noticed here? In order to make this work, I would actually have to start on 0. Do you see why? Because the only way that I could get 5 there would be if that were 0. So another way that you could write this then, if you wanted to start at 1, we would have to do I plus 4. Because it would be 1 plus 4, 2 plus 4, 3 plus 4, etc. And that one can still go up to infinity. So 2 different ways to write the same one. I would take either way. Just be careful that you watch for those things. Okay, and then the last thing is, how do we evaluate things that have index notation here? Index summation notation. And the way that we do that is very similar to the way that we did the sequences. We just follow the directions. So, for example, on this first one, it tells us that we want to evaluate 3 plus k squared from 4 to 8. And remember, we're only allowed to use integers here. That's our domain. So that means that we're going to plug in for k, we're going to plug in 4, 5, 6, 7, and 8. And then whatever we get, we're going to add all of those together. So I have 3 plus 4 squared plus 3 plus 5 squared plus 3 plus 6 squared plus 3 plus 7 squared. I'm going to run out of room here. Plus 3 plus 8 squared. And we're just going to work all of that out. 3 plus 16 would be 19. 3 plus 25 would be 28. 3 plus 36 would be 39. 3 plus 49 would be 52. And 3 plus 64 would be 67. And then, then you would add all of that up. Gosh darn it, I just deleted my writing. But whatever those 5 things were that we had going there, you would add all of those up, and you'd get your final answer. So let's look at this next one. 8i from I equals 1 up to I equals 5. 8 times 1 plus 8 times 2 plus 8 times 3 plus 8 times 4 plus 8 times 5. Obviously, I cannot give you an infinite series to add up here. You'd be at this all day long. So I'm going to have 8 plus 16 plus 24 plus 32 plus 40. And I get, let's see, 40 plus 40 plus 40, 120 is what you get, I think, for that. And so you would work out all of these exactly the same way. I'm going to skip C, but I want to draw your attention to D. How would I evaluate this? I want to evaluate from term 1 up to term 34, but all I have here is the number 1. So if there's nowhere for me to put in my input, that means my output is always going to be 1. So for the first term, my output would be 1. The second term, it would be 1. The third term, it would be 1. All the way up to the 34th term, which would be 1. If I do this 34 times, what am I going to get? 34. So that one's kind of a trick. Alrighty. The last thing that we have here is these formulas for special series. Okay, so if you see one of these things, instead of having to actually work them out for every single term, you can use these formulas. So the sum of the first n terms of 1, that was that last example we just did there. And you notice that if we did it 34 times, we were going to get 34. Well, that's the idea here. If I want from 1 up to n, the answer is going to be however many times I was told to add them together. That's what we get. The sum of the first n positive integers, which would mean 1 plus 2 plus 3 plus 4 plus 5 plus 6 and on and on and on, is always going to work out to be n times n plus 1 over 2. Don't forget, n is your sequence number, or in this case, your series number. That's what that n stands for. Which term in the series are you going for here? And, lastly, the sum of the squares of the first n positive integers. 1 squared plus 2 squared plus 3 squared plus 4 squared, on and on and on and on, is going to be n times n plus 1 times 2n plus 1. Okay, so these are kind of simplified here so that we don't have to do that away, and we can look at much larger numbers. This is the first example, the sum of n terms of 1. In this case, we're doing 8 terms of 1. So following the formula, the answer would just be 8. This second one, whenever you just have a variable here, that's the integers, the positive integers. And we want to go from 1 to 21. So 21 is what we're going to use for n. So, whoops, I dropped that. So it's going to be 21 times 21 plus 1 divided by 2. And that's what we're going to work out. Do your order of operations, parentheses first, so I get 21 times 22 divided by 2, and when we work that out, we get 231. So if you were to take the numbers from 1 to 21 and add them all together, 1 plus 2 plus 3 plus 4 plus 5, all the way up to plus 20 plus 21, you would get 231 for your answer. And lastly, whenever you see just the variable squared, that's this last formula, that's the sum of the perfect squares, in this case from 1 to 10. So 10 is the value for n that we're going to use. And it goes like this: 10 times 10 plus 1 times 2 times 10 plus 1, all divided by 6. Now this formula seems kind of random, but you can prove it. You can prove that this is the pattern for all the perfect squares. You probably don't care for me to show you that, so I won't, but you can just trust me on that. So we have 10 times 11 times 2 times 10 is 20, plus 1 is 21, and then we will divide by 6, and when we do that, we get, it equals 385. My writing all just disappeared again. I clicked the wrong button, but that's what you should get. Now, realize that because you're adding up integers, your answer should be an integer. You're never going to get a decimal for these. So if you do, that means that you've done something incorrectly. If you're only adding up integers, you're not going to get any rational parts, meaning decimals or fractions. So that should be it. Okay, that's where we're going to stop for today. Guys, I know this is hard. Trust me, this is hard for me to wrap my brain around, and it's a lot of formulas. Just take your time, go slow, and use your notes. Okay? All right, good luck.